Okay, so thus far we've talked about various complex quantities, things like the loss and storage moduli, the loss and storage compliance, as well as the loss tangent. And we mentioned things in passing like that the loss modulus is corresponded to the amount of energy dissipated in hysteresis due to cyclic loading, but we haven't really shown that. So what I want to do is to kind of cast these complex quantities now in the context of what they mean in terms of energy dissipation and energy storage. Okay, so let's go ahead and just consider a cyclic load. So let's go ahead and consider the implication of oscillatory loading on energy dissipation. Okay? So let's think about the elastic case first. Not the viscoelastic, just the elastic. So in the elastic case, here's our stress-strain axis. So there's strain and stress. If I cyclically load this material, I load up this curve and I load back down the same curve, right? There is actually no energy dissipated, right? I store energy and I then recover that energy, but I don't dissipate any energy. So in the elastic case, no energy is dissipated. Okay? How about for the viscoelastic case? So in a viscoelastic problem, so here's our stress strain, right? We have something that looks maybe like this in cyclic loading, right? And this area corresponds to the energy dissipated. So call that delta W, and that's going to be the energy dissipated per cycle, also per unit volume. Okay, so that's characteristic of a viscoelastic material. Okay, so how about we compute delta W? Okay, so to compute delta W, we're going to integrate over the whole curve, over the cycle. Okay, so what that looks like is that delta W, that's the energy dissipated, would be equal to the integral over the cycle times sigma d epsilon. Okay? What you'll find is that, of course, if we cut the cycle in half, there'll be this quantity won't necessarily be zero, but if we follow the whole cycle, whatever goes up has to come back down, and in aggregate it will sum to zero in the elastic case, but it's not going to in the viscoelastic case. Let's call that equation 1. Okay? So how about solving this? Well, via the chain rule again. So via the chain rule, we may write that delta W is equal to now the integral over the period of the oscillation, we'll call that T, capital T, of now sigma, and this becomes d epsilon dt, right? Let's call that equation 2. And I'll just say where T is one period of the cycle. Okay, so now let's suppose that we have some sort of a strain input, okay? An oscillatory strain input. So suppose we have a strain input, and that strain input is going to be given by epsilon of t is equal to epsilon naught times the sine of omega t. Okay? We'll call that equation 3. Okay? We've shown previously that the resultant stress is going to be given by sigma of t is equal to some sigma naught value, right? Now it's going to be shifted by our loss tangent delta. So sine of omega t plus delta, right? Let's call that equation 4. So I'm going to go ahead now and substitute 3 and 4 into equation 2. Okay, and when I do that, I'm going to get the following. I'm going to say delta W is equal to the integral from 0 to t of sigma, which is just going to be sigma naught times the sine of omega t plus delta, right? And then d epsilon dt, I have the constant epsilon naught that I'll just pull out. And then, of course, I have a derivative then of the sine of omega t, which is just the cosine of omega t times the derivative of what's inside, which is just omega. So I have an omega that comes out, and then I have cosine omega t dt. So let's go ahead and keep on trucking. Pull out the variables that are either constant or are not dependent on time. We have then that sigma naught, epsilon naught, omega, now times the integral from 0 to t of sine omega t plus delta times the cosine of omega t dt. Let's go ahead and call that equation 5. Okay, so what are we going to do here? Well, we're going to rack our brains back to high school now and recall some trig identities. Okay, so let's say we recall a trig identity, right? And that trig identity says that the sine of omega t plus delta is equal to the sine of omega t times the cosine of delta, right, plus the sine of delta times the cosine of omega t. Okay? So we can substitute that into equation 5. So substitute into 5. Okay, and now we have that delta w is equal to, we have our constants out front, sigma naught, epsilon naught, omega, now times the integral from 0 to t of this quantity here. I'm gonna bring the cosine of omega t out front from up there, and then write our trig identity term here, which is sine of omega t times cosine of delta plus the cosine of omega t times the sine of delta. Okay, dt. And I can split that into two integrals now. So sigma naught, epsilon naught, omega times the first integral, 0 to t, now of cosine of omega t times the sine of omega t times the cosine of delta dt plus the integral from 0 to t of the cosine squared of omega t times the sine of delta dt. Okay? I'm going to put a parenthesis around here to separate that so you see that this interior term is dependent on time. This cosine delta is not dependent on time, so we could pull it outside the integral. If we integrate cosine times the sine of over the period from 0 to t, we have two orthogonal functions, so their inner product is identically 0. So this term is identically 0. And we're left with delta w is equal to sigma naught epsilon naught times omega. Let's pull out the sine delta now and say sine delta now times the integral from 0 to t of cosine squared omega t dt. Okay, let's call that equation 6. Okay, so now we need to use another trig identity. So let me say recall another trig identity. Okay, and that trig identity said that 2 times the cosine squared of omega t is equal to cosine of 2 omega t plus 1. Okay, so substitute that into 6. So if we substitute that into 6, then we can write delta w is equal to our constants out front, epsilon naught, sigma naught, omega, sine delta. Now we have this quantity here that is the integral from 0 to t of, let's see, looks like we have a 1/2 here, times the cosine 2 omega t, right, plus 1/2. Okay, dt. So I'm now integrating the cosine. Now, since I've added a 2 in there, right, I've increased the frequency, so I'm now 0 to t goes over 2 periods of this quantity, but Whether I integrate the cosine over 1 period or 2 periods, if I integrate it over some integer number of periods, that term goes to 0. So this goes to 0, and I'm left with the following: epsilon naught sigma naught omega sine delta now times the integral from 0 to t. I have 1/2, I'll pull it out, dt, right, which is just equal to, this is just t over 2, right? So I'm left with epsilon naught sigma naught omega sine delta times t divided by 2. Okay? Let's call that equation 7. Okay, well, what is t, right? T is the period, and that's related to omega, the frequency, right? So note, we can write t in terms of the frequency, omega, right, as, let's see, so it looks like t is going to be equal to 2 pi divided by omega, right? Or looking what we need to substitute here, we can say that then t divided by 2 is equal to pi divided by omega. Okay, call that equation 8. Now substitute 8 into 7. So substitute 8 into 7 to get the following. Now we have the energy dissipated during a cycle, delta W, is equal to epsilon naught times sigma naught. My omegas cancel out. I have a from here and here, so those aren't there. I'll bring out the pi out front. Now times just sine delta. Let's call that equation 9. Okay, let me also remind you how we defined our loss modulus, right? So recall one definition for the loss modulus, which was y double prime, right? Which said that y double prime was equal to sigma naught divided by epsilon naught times sine delta, right? Epsilon naught is the value that we're applying. Sigma naught, remember, is had this magnitude of the complex modulus incorporated into it. Okay. Okay, so let's call that equation 10. Right. Or we could also say that this implies then that that sigma naught times sine delta is equal to y double prime times epsilon naught, right? So we have a sigma naught sine delta up here. So we're going to replace that and say that so we substitute 10 into 9 to get the following. To get that the energy dissipated delta W is equal to now pi times epsilon naught, the quantity squared, times y double prime. And I'll remind you, y double prime is a function of omega, right? So what does this say? This says, right, that the energy dissipated during a cycle is proportional to the loss modulus. Okay, so that's the first important conclusion that we've come to. Okay, so that's the energy dissipated during a cycle. But we want to ask the question, how much energy is stored during a cycle? Okay, so that's actually a more complex equation to solve, so I'm not going to do it here. I'll just give you the reference, okay? I'll just say it can be shown that, and the author is by the name of Tschogl, T-S-C-H-O-E-G-L. So he's got a fairly advanced Viscoelastic book that will, textbook rather, that will derive this for you. But it can be shown that the average energy stored, okay, per unit volume in a cycle, right? Because during the cycle we're changing how much energy is stored, and it's additionally complicated by the fact that our stress and strain aren't in phase, so it becomes a kind of a challenging problem to compute. So I'll just tell you what the answer is. It's given by a very simple equation that's very hard to get to, which I'll just call Ws for energy stored, is equal to y prime, that is the storage modulus, right, times epsilon naught squared divided by 4. Okay, we'll call that equation 12. Okay, so what's the upshot here? That the energy stored during a load cycle is proportional to the storage modulus. Okay? And now you might be asking, well, we've done storage modulus, we've done loss modulus. How is the loss tangent involved here? Well, let's think about this. Okay, so the ratio of the dissipated energy to the stored energy is called the specific loss. And it's given as follows. So this now will be delta W, the energy dissipated, divided by Ws, the energy stored, which is going to be equal to equation 11 divided by equation 12. So pi epsilon naught squared y double prime divided by epsilon naught squared times y prime over 4. Epsilon naught squareds cancel out, right? And I'm left with 4 pi times y double prime divided by y prime. You remember what this quantity was given as? By definition, that quantity is tan delta. Okay, so this is 4 pi tan delta. Okay, let's call that equation 13. So what we've really done is now define the physical meaning of these kind of 3 key complex parameters for describing viscoelastic behavior. So just in summary, here's the physical meaning of these complex parameters. Okay, so obviously we have y prime, which is the storage modulus. Okay, it's going to be proportional to the amount of energy stored during a load cycle. Okay, we have y double prime, which we said was the loss modulus, right? And that's going to be proportional to the energy dissipated during the load cycle. And we also now have tan delta, which is our loss tangent. Okay, and what is it going to do? It's going to be proportional not to the energy stored or dissipated, but to the specific loss during the load cycle. Okay, so those are the 3 key parameters to describe oscillatory loading in viscoelastic materials and what their physical meanings are, so you kind of hopefully now have a better sense of why we call those things the storage modulus, the loss modulus, and then the loss tangent.